The idea is actually.
So this section is going to involve a minimal amount of math and actually more older math, stuff that you've seen earlier in the year, come back again in this chapter. Aside from that, it's going to be very theoretical. Now, that's not to say that these concepts today cannot be mathematically interpreted, and they can. And if I talk about it all the time, if you study like science or engineering in college, these topics are their own classes, like literally. Modes of heat transfer, mainly today we're going to talk about conduction, convection, and radiation. All three of those things as a whole really go into a class called heat transfer in college. And you take an entire course on this one section alone. So I keep talking about that, how that's important that you realize that we're really just on the surface right now looking at what these things are. But if they interest you, you should really consider this as a field of study, okay? Especially because this is a field that is becoming more and more prominent, right? Think about heat transfer, think about the earth and heat. So like it's something that engineers in this field are going to be very widely sought after in years. They already are. So we've already defined heat really, we'll talk about it again. We'll talk about it with thermal equilibrium and then the applications and the modes. So first, the energy transferred between objects because of a temperature difference. That's the definition of heat. So it's kind of a weird thing because you could say like, turn the heater on, right? You call it a heater, I guess radiator in this case would be, but turn the heater on your home. A heater, what is it really doing? It's causing one element's temperature to get very high. So as a result, the entire ambient room is a lower temperature. So the higher temperature coils naturally have to give off energy to the other areas around it because it's an exothermic process, because it's at a higher temperature. So heat as a definition is really just if there's a temperature difference. That's what heat is. When you did this yesterday, you were demonstrating what heat is. A temperature difference causing energy flow from your hand into the desk. Okay? We talked about this yesterday, I think, already, but this is what's physically happening here. So, if we take a look at this, start with part A. The temperature in the water is very cold. You're inside of a cooler, an ice cooler. The temperature of this is a can of juice, which I haven't seen cans of juice in years, but maybe a can of soda, at 45 degrees Celsius. So when you look at this, you think right away, well, this object is getting colder, but the direction of energy transfer is outward from the object, because it has more energy than the surrounding water ice bath that it's sitting in. So if you look at this on a molecular scale, we think about this as the average kinetic energy of the particles in the can are vibrating at a higher rate than the actual atoms in the can themselves. Sorry, this is the actual juice. The atoms in the can themselves, and then the water molecules themselves. So the water molecules are the coldest here. So what this image is trying to demonstrate is that these are moving the slowest. These are moving a bit faster in average kinetic energy. It's not really moving. You know, follow what I'm saying? But the idea of a solid is that the molecules are vibrating at some frequency. And these ones are bouncing around, these little atoms in the actual juice itself. So you have higher kinetic energy, lower kinetic energy, the lowest kinetic energy. Because really, average kinetic energy is just the definition of temperature. Okay, it's just the definition of temperature. Now, if we slide over a bit, and look what happens after a little while, we notice that these two things come into equilibrium at a temperature of 11 degrees Celsius. Now, in the next section, we're going to talk about how to determine that value, and we're going to be able to do that mathematically. Okay, in the next section we'll do that. But for now, recognize that the 11 is somewhere between 5 and 45. Right? Take a look at the difference. We started with 5 and 45. They've got to meet somewhere in between. Why do you think they met at 11? Why 11? What's the significance of that value? Not exactly, but around. Why is it around that value? Go ahead, George.
Well, is it because it's easier to lose temperature than gain it?
It's very possible, and that's based on material, though. That's a good statement. It is possible that in this case, it's easier to lose the heat or lose the energy than to gain it because of the two materials and their specific heat capacities. That's very possible. But there's also another reason besides that. That's a good idea. Because that's absolutely possible. It depends on metal, and metal does have a higher specific capacity than water does. So it will lose energy more readily. Why else? Why is the temperature, though, not halfway in between, right? That's really the question. That's what George was getting at. Why isn't the temperature that they're meeting at the average of these two numbers? Why isn't it at 25? And 25 is the average of these numbers. If you've taken an ice cooler or a cooler filled with ice and put a can of soda in, that can of soda gets pretty cold pretty quick, right? Does the ice get pretty hot pretty quick? No. Why? Come on, use common sense. It's more common sense than anything else.
Well, there's more water in there.
Exactly. There's more ice bath solution than there is one can of juice. Think about mass. Remember? Q, you're going to learn this next section. You've learned it already. Q equals mc delta T. M stands for mass. If the mass of the body is greater, its ease of losing energy is not as high. It cannot lose energy as readily as something else with very low mass. That's why if you take like a pellet, like a bullet almost, that was heated up and drop it in a bath of water, you'll hear it sizzle, right? And it'll cool off pretty quick because it's in a bath full of water, or a mass of water, or anything else. So the next slide.
So I'm going to try, except this is close to the one back. Yeah, the one for everything else is ready.
So these are the temperatures right?
That's right.
Oh, out here.
Yeah. No, not in there.
Okay, so the Wi-Fi. My desk, the second drawer of my desk on the left side is the post-its. They were bringing it on one of them says that question Wi-Fi or something like that. It's the access code for it.
All right, thank you.
All right. So we're going to look at quickly just units of heat. All right, the idea of units of heat. What do we use? What do we use for heat here in the U.S.? I can tell you we use two of these. Anyone guess we use which two there? One you use all the time. Calorie. Right? Because when you eat something, you're eating something that has mass. Network name first, Anthony. You need.
Oh, this just has the LabQuest user and password.
Loyola Computer, all caps.
Loyal computer.
All caps. So we use calories with food because when you eat food, what do you gain? You gain energy. That's why you eat, right? For energy, or else you would not be able to sustain life. George?
Kilocalorie.
Kilocalorie is the other one, yeah, for sure. So calorie or kilocalorie, and our calorie is actually this one, the capital C one. It's the one we use for food and nutritional science. But we also use BTUs. Have you heard this phrase before? Never? Okay, well, all it is, it's another rating of the amount of energy conversion from joules. So if you knew that something created a certain amount of joules of energy, you could convert that to BTUs. And here's your conversion factor. So if you buy an air conditioner or install a new heating unit in your house, we'll talk about how many BTUs of energy it will produce in a given time period, which is usually really a power rating, right? Think about it. Power is energy per unit time. Power is energy or work over time, energy over time. So BTUs over a certain time period is what you would have as rating, which is really the power that we give. So BTUs is energy, BTUs per certain time unit is power. Let's see. So let's talk about the next slide and do a quick mathematical example. So remember when we looked at a circuit and the charge carriers exited the battery, they had a lot of what? When the charge carriers exit the battery to go into the circuit, they had a lot of, which kind of energy we call it in that case? It was potential energy. We said that the charge carriers had high potential. And then they hit the light bulb, and what happened? It used up all that energy, the light bulb. And then it went back to the battery with no energy. And then the battery, what happened when it got to the battery? Did it break? Or did it go into the ground?
Yeah.
Be careful, guys. Yeah, close that up if you can. Some people have been leaving those open. Yeah, there you go. No, I did that once, actually. My ankle didn't feel it. So, if we think about low potential, how does it get back up to high potential? What did we say? There was a phrase we used.
I forgot what the phrase, but it was like replenished with electrons.
Okay, the battery replenished it with energy, agreed. And we said the battery did work on the charge carriers. It was a phrase I used. And although it sounds very ambiguous, and even now I'm thinking about it, I'm like, man, when I was in college, this was so annoying. But professors used to always say, if we're not really certain about what's physically happening because it's a chemical thing that's occurring and maybe we're not chemistry majors, we say in general that the object did work on something and it raised its energy level. It's almost like an ambiguous way of saying, I'm not really sure how this is happening, but this is what physically happens. Now, with a battery, it's chemical conversion. You're taking chemical energy and converting it into some sort of electrical energy. But personally, I took chemistry in college, but I didn't major in chemistry. Mr. Joseph will probably tell you exactly what physically happens there. But I say it just does work on it. Same thing here. You're changing the internal energy of something, you say you do work on it. But it's a little more physical and it's easier to see if you think about this, if you think about exercising. When you go from the ground floor to the fourth floor, how many of you have run track at school or something where you've done the stairs before in school? Excellent. Do you guys do stairs sometimes? Okay. Stairs are worse because what are you doing? You're changing the amount of, you raise elevation, you're changing your potential energy. The amount of potential energy that you change by, we said, is the amount of work you do. So physically, if you want to compute how many calories you burn, let's do an example. Let's say you go from the ground floor of Loyola, you're 80 kilograms, jot these down, you're 80 kilograms, you go from the ground floor and up here, which is hypothetically, let's say, 20 meters, about 60 feet. So you go 20 meters in elevation, and you're 80 kilograms. How many calories do you burn? Figure that out. How many calories do you burn? And you have to use the conversion on the previous slide to figure out calories, but you know your mass and you know the change in height. Alright, so can you start recording data now? Put them in, put the tops on, and then I'll connect it.
The plus button or the play button?
I'm assuming I've never done this. Run a test one right now. Run a test trial. Hit play right now. No, without even anything on, and then stop it, and then rerun it.
It looks like it just records the temperature over time. Should I use that?
That's fine for both, though, right? Both temperatures.
Yeah.
Perfect.
Alright, so should I start it?
Yeah, you can start it whenever. It doesn't have to be showing up here. So as long as you're recording data when you put it in. All right. So I'm going to pause for a second. Actually, you guys, let's finish this problem. Then I'll bring up the data instead of doing that. So we got 80 kilograms moving a height of 20 meters, just up the stairs once. We want to know how many calories you physically burn. So we'll convert it from joules to calories using the last slide once you get the numbers. So this is why I said you're going to use a little bit of old math. Okay, you're using old formulas to do this. Using old formulas just to do this. What do we get for a number here? What do we get for a number? Yeah.
15,696.
15,696?
Yeah.
Agreed? Somebody? Yeah? All right. Now, what's the conversion from the previous slide to get 15,696 joules into calories with a capital C? The capital C calories.
4.186.
What is it?
4.186.
Which way? You got to give me units. So what does 4.186 mean without units? 4.186 joules is calorie or calories is joule? 4.186 joules. Are you sure?
Oh, no, 4.1
Yeah.
times 10 to the third.
I was going to say, because that's going to be a ton of calories. It doesn't make any sense. Times 10 to the third is one capital C calorie, which is the food nutritional calorie unit we're thinking of. Okay? And this is not to get you guys to be like calorie freaks. You be careful with getting obsessed with calorie counting. What do you get as a value here? I mean, you're pretty much dividing it by 4186, right? So it's about 16,000 divided by 4,000. Right? 16,000 divided by 4,000. I'm guessing it's 4. Is it around 4 the answer? What is it? 3.75. So you go up and down, or you go up the stairs rather, not up and down. Up the steps from the bottom floor running up, that's 4 calories on the way up. You think on the way down it's the same amount of calories?
No.
Probably not, right? Because you're really not, I mean, you are still burning energy actually, because just the motion of your legs doing this, going down the stairs, but you're going down in potential energy, so you're not really doing all the work that you did on the way up. Gravity is actually helping you. So on a round trip, maybe you burn 5 calories on a round trip. How many do you do for basketball?
12.
No.
12?
It was 10, but it was like
So 12, think about it, that's 60 calories right there. 12 of those things back and forth. Yeah, that's it. That's a decent amount actually, I think. How long does it take you to do 12 of those?
You probably do it in 10 minutes. You run them down.
So 10 minutes, 60 calories. I guess running a mile is better.
What if you like weight it down too?
Yeah, that's
the weighted
what does it
You do it
increase?
with the weighted ball.
Yeah, we do it the way it's going.
So this is probably more than 80 kilograms. 80 kilograms is about, 80 kilograms is like 180 pounds actually.
Yes.
176 pounds.
We do around 10, then we come back. Mr. Johnson says Trooper and I did around the 4.
Stand up. All right. So we've got 3 modes of heat transfer. Let's start with the first one, conduction. Now, this is a perfect segue into what we're doing over here. So let's focus our attention on the side of the room now for a minute. So I'm going to have you explain what we're doing. You might want to do that. Actually, to run all the rest of
Yo, last night before I went to bed, of course I wanted to. Did you get that seed boy? Did you get that channel?
Yesterday? I did, but I don't think that's the cat. And then I didn't even like shoot, but I had to eat like I loaded that's real picture, but I still have like whole
He was grossed out.
They tell you the bottom.
2 samples.
I think I did it on that time.
Yeah, but it's like, no, you could like see it.
Yeah, I did. Honestly, hopefully by next year.
Next year, around this time. Because that means we cold lights is going to be a senior. That's what we better be on track.
Guys, please. Okay.
Alright, so in this one there's cold water, there's some ice in it. And this one over here is filled with hot water, so I ran over the microwave, there's fire served. So here it's connected here by this metal, this pipe. And here there are 2 little prongs in each one that are recording temperature here. And so we have it to collect the temperature of both of these over like the next however many hours. And you'll see over time, the heat transfer, so this one will actually cool down while this one heats up, and you'll see over time it will slowly, come to meet the middle.
And what is it going to reach eventually? So, yeah, ask a question before
I was going to say.
Okay. See, the metal heat pipe, metal is a good conductor of not just electricity, but heat also. That's why we're leading this into the next segment here. See the red end of that metal piece, or the specimen on the board? That's showing a lot of high heat. It's a temperature gradient. On the right end is blue for cold. It's literally what you're seeing here. If you actually, when you do this, if you want to, you don't have to get up everybody at once, but if you want, you can see this is ice cold here, and this is actually very hot. So you can literally feel the difference. If I took, let's do it. Did I use this yesterday, you guys? No, you didn't have it? I forgot, yeah.
I feel like Elliot has one, it's just for some reason.
He probably does, yeah. So it's an infrared thermometer. So I could just These are your skin. It's the temperature. You're 86.7 on the skin right now. It's crazy. Everybody's different temperatures. George, let's see. George, 85. Oh, no, I'm sorry. It's Calvary. 89.5.
Oh, he
This is what happened yesterday. 86.
Oh,
Here's I know, sure. Your hand has a tendency to be cooler. I think I have a temperature of 90 degrees. That's not good. Yeah, I've been feeling sick. I gotta be careful. Let's see your hand. Yeah, 78.2. Hands, your extremities are always much colder. So I was on like on your fingers. Anyhow, so let's see if this actually works. I didn't do this yesterday because we didn't have this set up. So we've got, so we want to jot these down? From left to right on the diagram, from left to right. So the high temperature first.
0.
All right, 77.5. Sorry, here we go. Let's try that again. Okay. 86.
Wait, what?
The hot one
This is on.
Guys, this is 86 first.
I think it said 77.
I know, I was on the wrong side. 84. 75. Just jot these down in order. I'm moving about a setting here every time. 73. 70.5. Little spider. No. 70.1. 67.3. 65.5. So all you're seeing there, honestly, all you're seeing is the temperature gradient change, right? So what was the highest temperature lows? Yeah, 86 to 65, 20 degrees Fahrenheit temperature change between the two different types. Now, if instead of metal, we had used something like, I don't know, plastic, do you think the same thing would be occurring right now? How would it differ if you used plastic? George?
Would there not be as much of a difference from the highest temperature to the lowest?
Most likely, the ends wouldn't heat up as much because they're not good conductors. What else?
Wouldn't also like the plastic
If it was hot enough, let's assume the plastic can't be melted. Let's say it's something made by industry to, take on hot temperatures and cold. What else do you think? I'm thinking that more of it would be room temperature. So follow me for a second. How many of your data points were between 70 and 73 on there, Julia? 2 out of how many? 7. Okay, so out of the 7 total data points we collected, 2 of them were in the room temperature range. For something that's plastic, the very ends would heat up, but it wouldn't transmit as easily. It's not a good conductor, right? So more of that, more area of the metal bar that you're seeing, that little bridge, would be room temperature if it were plastic. The heat transfer that's occurring occurs very readily with metal because it transmits by vibrations. These molecules vibrate higher frequencies, causing heat to spread or propagate down the metal specimen. That's what's happening here. If it were plastic, the middle would be all, I would probably say that like 5 of those temperature points would be near room temperature and only the extremes would be outside the range of room temperature. So you would have smaller, what's the word for this? I'm trying to think. It's a gradient. A temperature gradient is the word. It's a change in temperature, really. So you know how you talk about slope with a graph? The slope of this goes from a higher temperature to a lower temperature over a certain distance. It's like a slope. It's a temperature change over a given distance, and you call it a temperature gradient. So there'd be a smaller temperature gradient if this material were not as conductive. God bless you. If it were not as conductive as metal is. We have something called the conduction coefficient. You don't have to really know mathematically anything about it, but it's a symbol K. You don't have to really be familiar with the letter K, but just so you know, that there's something called the conduction coefficient. It's a material property. George. Yep. It's delayed, thank you. Give it a minute. K, I wrote down the material property. K is a material property, similar in nature to density. Similar to density. The density of lead is a given number. It doesn't matter how much lead you've got. You could have a small piece of lead, a big piece of lead. The density is a number. It doesn't change. The mass changes if you have more of it, right? The volume changes if you have more of it. But the density is an inherent property. Next stop. The density is an inherent property. Okay? Just like here, the conduction coefficient is a property of the actual material itself. Okay, the actual material itself. If you have a higher K value, it means that it can more easily transmit heat. In general, we say that metal is a good conductor. Other materials act as thermal insulators. Thermal insulators. Air. Air has a very low K value. So most windows, these are most windows now that are produced, what do you notice about how many pieces of glass there are? Anybody notice this about new windows, not old windows?
Aren't they usually double pane?
Yeah, double pane. Very good. That's the word and everything. They're double pane windows. Now, between those panes of glass, glass is actually a very poor insulator. Glass, although not being metal, readily transmits heat. So if you have a single pane of glass, the heat that's in the room in the wintertime can easily escape through that glass. It's drawn, believe it or not. So just so you know, here's the room. Here's the pane of glass. Here's the end of the pane of glass. If it was a single pane of glass, this out here would be the outside environment. That's how you would draw it. And usually you draw this as like a resistor. You draw it like that to show it's not even there, of course. Is that why you were looking at me funny? It's not showing up. You draw like a little squiggly line as a resistor. I'll try and zoom in. Hopefully it'll catch up in a minute. You draw it like this. So the room is here. You have a pane of glass, and then the environment's here. But with most windows, since they're double pane, there's actually a thermal barrier, which is really air. Still nothing, no. All right, let me just reconnect the AirPlay. Hold on. Recording. Every building for a long time had asbestos. It was accepted. It was used as a thermal barrier insulator because it had a very, very low K value. It was mainly these fibers with air between them. That's pretty much what like a double pane window is, trapping air. But some windows actually use, I think if I'm right, I think it's argon gas. Argon has a lower K value than air does. So you use that instead of air now in between the window panes. But yeah, almost all buildings did for a long time. Because this is a historic building, it did. Absolutely. It's removed though. They removed them from walls a long time ago. It was like a big deal. They went into homes. You have to actually break into the wall, get all the asbestos out. People got sick. They had to wear masks when they were using it.
Didn't it emit like radon or whatever it's called?
I don't know what it was. It was some sort of a, what's it called? When it's an air particle. A particulate, I guess? Is that the word? When it's a particulate in the air that you can get, it's airborne pretty much. Okay? Yeah, I don't know. I don't know what the new insulation is. I'm sure it's something that's been tested widely that it's not. Well, I don't know. Is that what it is? Yeah? That's different. I know what you're talking about. The stuff you put on the concrete slabs and level the concrete slabs. You saw that on Facebook or on some sort of social media. That video went viral like 2 years ago, right? You know what I'm talking about? Yeah. It's really cool, actually. That's a different thing, though. That's not for thermal insulation. That's for structural support. That stuff is really cool, isn't it? Have you heard about this? It's like this foam stuff that they've used in the city all over the place to level unlevel concrete slabs. When you walk in the city, isn't it really annoying when there's a tree and the tree roots lift up the concrete slabs and you're walking and all of a sudden you do one of those? I feel like all you've done at some point. Anyway, They have this foam that you can actually use now. It's some sort of a polymer, is the word for it, that has properties that it can literally lift up the concrete slab. And they inject it like a needle would, and use a plunger or a mechanism, it's really a pump, to pump this stuff underneath the concrete slab. And you'll see the slab literally realign itself based on where they're pumping this. It looks like, what can you describe it as? You know what it looks like? It looks like that stuff on science experiment shows when they combine like a liquid and this like powder, and it becomes like this fluffy stuff that overflows. Do you know what I'm talking about? It gives off heat. It's an exothermic. What? I don't know. I'm not sure what they're using these days. I'm not sure. You can look it up. Find out. I know this much. And thanks so much. I should next time just get up and go. I should have told you. Sorry, 5 minutes ago. Are you in the other sections?
Yeah.
Are you not in school?
No, because I have
It's already started.
Alright.
Yeah. If you're not in school, then don't worry about it. We're just watching a video in the second period. There's like 2 more slides for this, so if you want to get the notes or just look at the last bit of the video. Okay? Yeah, take a quick bathroom break. Go ahead. We'll come back. All right. So second mode. So first mode was conduction. Conduction involved contact. Okay, let's remember that for the last mode. Conduction involves contact. The molecules are literally in contact. You touch the table, heat is transferring from your hand to the table by conduction. This is the second mode now, known as convection. Convection involves a fluid. Fluids are defined as what? Either a liquid or a gas. So, if you've ever burned yourself before, what do you do right away? Cold water, or what do you naturally do if you don't have cold water? What do you physically do? Right, yeah. You shake it, or you go, like, ooh, on the hand, right? Or if food is hot, what do you do to the food? Why?
Conduction.
Not conduction, it's convection. Air, when you blow air over the fluid, it's over the food, it's a fluid flowing over it. Air is a gas. When you literally blow on food, you're running air over the surface. You're running air over the surface. Naturally, it cools that surface. Okay, it naturally cools that surface as a result. Air is just flowing over it. In this case, these are convective currents. Take a look. You're boiling water for tea. The water at the bottom gets hot. Why? Naturally, because the flame heats it up. The flame itself is really combustion, so this is really kind of gas here. So this is gas heating up the metal. The metal, using conduction, heats up the water. The water, using convection, flows upward. The cold water flows down, and this fluid flow creates heat flow. So this is a convective current. Convection ovens work in the same way. The air is heated at the bottom usually. It rises, the cold air falls, and then it continues in this cyclic pattern. Hot air rises, cold air falls every time. It's the same thing inside of an oven, what you're seeing right here. Okay, a convection oven is called that for a reason.
And so eventually it all becomes hot, correct?
Yeah, eventually the temperature is hot enough that the coils on the bottom, what do? The coils on the bottom, if it's an electric oven, or the flames, if it's a gas oven, when it reaches the correct temperature, what do? Yeah, they stop, or they naturally at least reduce, right? They reduce to something that can maintain equilibrium. Guys, an oven is pretty much an equilibrium container when you think about it. So is a fridge. A fridge, it will run, and it will run really hard until it maintains the given temperature. When it reaches that temperature, it stops trying to remove heat from stuff, but to maintain. And that's when a running fridge uses less energy than a startup fridge. We talked about that with electrical circuits. Same thing with an oven. It eventually kind of stops. It reaches equilibrium. The thermocouple that's in there measures the temperature, and it says, oh, the user tells me 400. I'm at 400, so I'm going to stop producing heat right now, or at least maintain that heat level.
So if it's like the more food you put in the refrigerator, the harder it's going to go?
Absolutely. Until this is a great example, because it's counterintuitive. At the start, yes. so he said, the more food you put in, the longer it takes to get to the right temperature, which makes sense. It's more mass. Q equals MC delta T. We're going to see in the next section. But until it happens that everything gets cold, then everything acts as like an ice block. So if you fill a fridge up, although it takes longer to cool everything down, over the long run, you use less energy. An empty fridge uses more energy. Think about that. Isn't that crazy? You would think that a full fridge uses more energy, right? Because you have to cool everything down. But over time, everything that's been cooled down in the fridge keeps its coolness in a sense. And it almost acts like a piece of ice cooling down the fridge itself. So although it takes a lot of energy to remove the heat from those things that you put in, once they get cold enough, they then act as like an ice cube cooling down the actual fridge itself. A stocked fridge in a deli uses less energy than an empty fridge in a deli. And you literally can see it. Like my dad owned a deli. If the fridge wasn't stocked, he would yell at me about it. And he would talk about it all the time. You know, and his like good friend used to run all of his HVAC in the deli. This guy Tony, and I knew him since I was like 2 years old. Tony does all the stuff in the fridge anytime anything breaks. And he would always tell me, say, Harry, keep everything full, because once it gets cold, those things act as if they're like ice cubes in the fridge, keeping everything else cold. So at the start, it takes more energy, but over the lifetime of it, it uses less energy to do it. Yeah.
Would you ever calculate how much energy you use by opening the fridge?
You would need a closed environment and then temperature change in that closed environment and then use Q equals MC delta T. But can you physically do that? Well, no. There's a lot of environmental laws and stuff. It wouldn't be a contained experiment. You know what I mean? Okay, it doesn't make sense to do it. You would have too much energy loss. For convection, just so you know, H is called the convective coefficient. Remember K from the last slide? H is the convective coefficient. It's a material property that describes how readily a fluid can transfer heat. For example, an air conditioner. What does it use? If your air conditioner isn't working well, the mechanic might say, you need to zap it with some, what's the word? What's the fluid that it uses? What is an air conditioner? Nobody knows this word? You never talk to your dad or your mom if either of them are into mechanics or if something breaks. Your car never broke down, the air conditioner in your car never broke. You have to refill the what?
I have to give it a jump.
You give it a jump, yeah, that's electrical though. I'm talking about the air conditioning unit only. Air conditioner. It's like pouring out hot heat. It's a fluid, yeah. It's not antifreeze. Antifreeze is something else.
That's for cars.
It's for cars also, but this is also for cars. Have you heard the phrase Freon? Freon? Freon is air conditioning fluid. It's known as R134A. It's a specific fluid that was made a long time ago that very, very, very readily can absorb heat. It can easily absorb heat. As a result, it absorbs the heat in the room. That's how an air conditioner really works. Although you think it's flowing cold air in, right? It's pumping cold air in. That's part of what it does. But it's actually removing the heat from a room. The actual refrigerant, R134A, has a very high H value, convective coefficient value. Okay, it's a fluid that can very readily absorb heat. And as a result, it removes the heat from the room. There's a fluid inside of there that flows through it. It absorbs the heat, which heats up the fluid. It then runs through a cycle that's powered by electrical stuff to cool it back down into a fluid. It then absorbs more heat. It evaporates. It cools it back down in a condenser. This is a thermodynamic process I'm going over. We're going to probably touch on thermodynamics right after this chapter. I think I'm going to do 11.1 this year, which I've never done before.
Is that what, like, sometimes, liquid drops?
Sure. Condensation. Yep. Condensation. And it's not the Freon that's condensing. That's just condensation on the outside because of the temperature difference. But condensation of the Freon occurs internally. It condenses back to a liquid, which can then absorb more heat, which melts it, which boils it off. It condenses back to a liquid. It can absorb more heat. So it goes through this process every time of absorbing more and more heat. Gabe, question?
So H is just how much heat something can absorb?
A fluid can absorb. Yep, a fluid. Okay, it depends on a lot of stuff. It really does. So there's a lot that we have to talk about. It has to depend on pressure. It depends on the buoyancy of the fluid. There's all this stuff, but I'm not going to get into that. There's a lot of math on each of these. Okay, in heat transfer, in the class I took in college, we spent like 2 chapters on each type. We've just spent like 10 minutes on each type just now. Okay, 8 minutes to be exact. We would spend 2 full chapters on this. So there's a ton of math involved It's a ton of heavy-duty calculus involved math. The third method of heat transfer we're going to talk about is radiation. Okay, radiation is very unique. It's very unique in that it involves particles or waves that travel through a medium. The medium does not have to have anything in it, though. It could be a vacuum. Think about that. How does the sun heat us up? It's not heating us up by fluid flowing from the sun to us. It's not heating us up by conduction, by touching us. So it has to be some other mode. That's what radiation is. The sun heating the earth, it's using energy in the form of waves. These waves are traveling, and these photons are carrying energy. The light itself is carrying energy toward us. And the light transmits energy when it gets to us via radiation. Okay, via radiation. The human body, yeah.
So like when you're on like let's say a beach and you're looking at the ground, you see the heat waves. Does that?
That's a mixture of radiation and convection, because it's actually the fluid in the air that's causing that little waviness. If there was no atmosphere or air around you and you were in a vacuum, you wouldn't see that. It's a result of both. The earth is radiating heat outward, yes. So it's radiation. But you're seeing the convective currents, the flows of air above. And that's a great question, what he's talking about there. It's a combination. The human body is a natural radiator. You know that, right? Your body literally gives off heat. We've been talking about the core temperature of 98.6 or under your tongue, yet skin temperature we saw was between like 80 and 90 somewhere. So clearly, we're radiating heat. We're giving off heat. Our body is losing heat outward. So what we're doing is we're literally reducing our internal energy level. We're giving off heat. We have to eat food to gain more energy. We then produce some sort of heat, because what does our body do to the food when it goes in? It digests it and says, you know what? Today you ate fruit this morning, really healthy stuff. I'm going to use that energy in a good way. But tomorrow, you ate a bacon, egg, and cheese, which I love to eat sometimes too. But you're getting you're not getting good stuff out of it. You're getting stuff that the body cannot use a lot of that energy. Okay, so when you use the energy of healthy food, you burn that energy off very easily. When you're using energy of unhealthy food, you usually store that energy. So you're thinking about energy as the total body's internal energy level. By giving off energy, you're replenishing your body with some sort of a fuel or source of energy, which is food. All right, stop there for today. There's a decent amount of questions. Most of these are theoretical, though. Okay, most of them are theoretical, so they're pretty easy to answer. They don't involve a